Today we start into our real journey into geometry, and we're talking about the building blocks of everything that we're going to make. All the objects, all of the shapes that we have in geometry. This is where they begin. This is how we're going to create them. So we have a lot of vocabulary today. I recommend you capture, as we go through these notes, all of these different terms and have your definition, a drawing, something that's going to help you to connect to these terms because it's a lot of vocabulary. So we start off with a thing called undefined terms, which to me sounds super weird. What it is undefined terms are these things called point, line, and plane. And it doesn't mean that those things can't be defined. It doesn't mean like undefinable terms. It means terms that are kind of like our starting point for building up every other definition within geometry. So we kind of have to start somewhere, and we start with points, lines, and planes as our basic objects within different dimensions. So we take those, we use them to determine or define other objects and other concepts. So they themselves don't need a definition. We define them just by understanding and examples, basically. I think it's super weird that they're called that. But you probably understand already what those three things are from previous math classes and just interacting with the world. So a point, a line, and a plane are objects. A point is basically a dot in space somewhere. It has coordinates. It has an x and y coordinate, or in 3 dimensions an x, y, and z coordinate. And it doesn't take up any amount of space. It has no dimensions. So no matter whether I draw it this big or that big or that big, a point isn't considered to have any width or height or depth. It's completely dimensionless. So a point has no dimension. So we could think of it as being a 0D object. So it defines a point in space, but it doesn't have length, width, or height, so it has no dimensionality to it. And we can express it in basically any dimensional arrangement. So like I could draw a number line, which is a 1D representation, and put a point on there somewhere. I could draw a coordinate plane with an x and y in a 2-dimensional, and we know we can make points in there. I can even make an x, y, z, and it's hard to draw in 2D, make a point in space and give it an x, y, and z coordinate. So points themselves have no dimensionality, but they tell us where something is. A line is a 1-dimensional shape. So line has only length, and it's 1-dimensional. So basically it can only go one way, and if you think of a point riding along a line, it can only travel in one direction, right? It can go left or right here, but like that's one line, one straight line it's traveling along. And no matter what direction we draw a line, a point that's on it can only travel that one dimension. It can't go perpendicular to that, or it can't go out of plane with that. So it basically is just stuck on that one dimension of a line. A plane has length and width, or whatever dimension. It has 2 dimensions. I think of it as length and width. And you know a plane by what we do with our coordinate plane, with the Cartesian plane where we have the x, y coordinates. So x is 1 dimension, y is another dimension, and we can give a point a definition that is some amount along x, like on the number line, but then we can bring it off of that line to some y dimension as well. So we can have something like 1, 2 as a point that has a x distance and a y distance. So one step up from plane, which this is actually considered a defined term, but I want to cover it here with these because it's basically just the next progression, is space. So space has 3 dimensions. It has length, it has width, and it has depth. or length, width, and height, or whatever you want to call them. I never know what thing to call those dimensions. So here we could add, basically coming off the page, we usually just draw that as like a diagonal, the z dimension. So think of that as this 1, 2, if I pull it above the screen, so pull it out of the screen toward you by 1 unit, then it would be 1, 2, 1 for its coordinates. It would have an x, a y, and a z to locate that dot in space, not just on a plane. So point, line, and plane are considered undefined terms, and we have ways of expressing them that differentiate them and tell us what's what. So a point is always just referred to by a capital letter. So point notation is something like just A. And you've seen that before. If I put a point on a line, I can call it A. Or you've seen a triangle and we draw it and we name its vertices, the corners of it. We could call it J, K, L. Each of those capital letters is the name of a point. So we can call it A, or we can call it, if we want to be really clear about what type of object it is, we could call it point whatever. But basically we just need a capital letter to refer to points. Lines have different notation. So line notation, we know from algebra and previous math that we can define a line by any 2 points. So once I have a point here and a point here on this plane that I'm drawing on, there's only one way to connect those 2 dots with a line. So I'm going to go connect those 2 with a terribly not straight line. And that is the only line that can connect them. So we can define a line by any 2 points. So if I had points M and N, I could call this line MN. But we can define other objects with 2 letters as well. So if I had a line segment and its endpoints were M and N, I could also define it with those 2 points, but I need to be able to know a difference between these. So we have what's called notation, which is just a symbol to show us that this is a line. And our notation for a line is a double-headed arrow. So over the top of MN, we put an arrow facing left and right that looks like a little line to tell us we're talking about this MN. One important thing with lines is they always have arrows on the end and they extend infinitely in whatever direction they're going. So just like on our number line we had an arrow left and right, that means the line never ends. That's what differentiates it from this other object called a line segment. A line segment has endpoints and it doesn't go on infinitely. So if you're drawing a line, it's very important that we put arrows at the end because that's what determines that it goes on forever. So sometimes we don't want to use 2 letters in this symbol. That's a lot of stuff. We can actually name lines a second way that's really simple. Next to the line, we can put 1 script letter. So script is like the curly cursive letters. So if I call this line L, I could just refer to it as L. I don't need to say line, I don't need this arrow. It just is the name of that line, and we reserve those lowercase script letters to refer to lines. So I can name it either of these 2 ways, and if there were other points on the line, if I had M, N, O, naming this line M-O or O-N or N-M, any combination of those 2 letters that are along the same line, they're all defining the same line. They're not different things. So I can name this line more ways now that there's 3 points on it. But this little script letter is probably new to you, so we want to know about that. So this is an L, but I could also call it like P and make like a little P here. I'm not very good at drawing script letters. Or like N, something like that. So any kind of script letter names a line. So planes, plane notation. You could think of a plane as being infinitely big 2-dimensional space. So kind of like a line goes on forever, a plane also goes on forever in 2 different dimensions. So when we draw our xy coordinate plane, we usually put arrows here, right? So the x goes left and right forever, and the y goes up and down forever. That's because planes are infinite, just like lines are. When we draw a plane on a paper, we typically draw it as like a parallelogram, so something like this, which obviously has edges, and we don't draw like arrows everywhere around it because it would be really hard to express with arrows. So it's understood that just this parallelogram shape represents an infinitely extending plane. So we show it as being flat like that, but really it goes on forever in those 2 dimensions, just like our xy plane. So to define a plane, we need more than 2 points, because 2 points make a line. But if I make another point off of that line, so somewhere like over here, that defines a 2-dimensional shape. And the most basic, smallest 2-dimensional shape we can define is a triangle. So once we have 3 points that aren't all on the same line, we've defined a plane by those 3 points. So M, O, and P define a plane. And we can name a plane by any combination of 3 capital letters that are the points lying on that plane. It doesn't have a special symbol like lines and line segments. So I could call this plane MOP, and that would tell us it's that. We could also, like the point, say plane MOP. With this, the letter order makes no difference. So whether I called it MOP, OPM, POM, all of those mean the exact same thing. So also, since M, O, N are all on the same line, I could also define the plane with these 3 points. I would get the same plane because these 2 triangles lie on the same plane. So I have very, very many ways I could name this plane now. Any combination of 3 of these letters that aren't all aligned with each other. So plane notation, just 3 capital letters. We can also use a shorter version like we did with the lines. And for that, we use a capital script letter. So instead of a lowercase l, I could do something like a big B. And that, I'm not, like I said, not good at drawing script letters, but we have fonts for that when we put it on a page. But capital B or like an A, capital A like that would be a plane name. So we can use 3-point names or a capital script letter. So these are our different ways of notating these objects, and we need to be able to recognize that if something says L, or a script lowercase letter, L, M, and whatever the letter might be, we are knowing that that's immediately talking about a line. So we know that lowercase script is line, uppercase script is planes. So those are our 3 basic objects. We want to talk about a few other concepts today, which are defined based on those. We already talked about space. Space is basically the set of all points in 3 dimensions. So it's where we exist. We exist in space. You could theoretically create higher order dimensions, like a 4th dimension, which is made up kind of how if you took every plane, like every flat plane, and stacked it together, you would come up with space, right? Just like if you take a bunch of flat lines that are all parallel and stack them up, you end up with a plane. You could theoretically take the space that we live in and stack it with other spaces and create a 4th dimension. But since we exist in 3 dimensions, we have no conceptualization of that. We have no way of understanding or conceiving of what that would be like beyond just kind of abstract. So space to us is everything. It's all points everywhere in all dimensions. So whether it's on the floor, the ceiling, outer space, all of those are points in space, and they have x, y, z coordinates. So we don't need to name space like we did with planes because there only is one space. Okay, so some defined terms, things that we define based on those others. Space was defined based on points. Collinear, it has kind of 2 points. It's weird because it has 2 L's in there, but if you can think of other words that start with we have like co-teachers, we have co-captains, we have coinciding. So like anytime coincidence, anytime that happens, it means together. So it's a prefix that means something is happening together. We're teaching together, we're captaining together. Co-pilot is piloting along with the pilot, right? So those are together, and linear obviously means a line. So collinear is just any points that are together on a line. So in the last slide we looked at 3 points. Here I'm going to do A, B, and C, and all of those lie on the same line. So remember, we only needed 2 of them to define a line, so if we add additional points along that line, we say that all of these points are collinear. So it means together on a line. So you can probably guess what coplanar means. Again, co means together, and planar means on a plane. So all of these are on a line together, but then remember last time we made other points out here and we could draw triangles. And since I'm drawing on a screen, I really can't draw anything in the 3rd dimension. So we could say all of these objects, I already have E, let's make that F, G. All of these things lie on the same plane together because they're all flat on the page. I would need some representation of 3D, we'll look at that on the next slide, to see something that's non-coplanar. So we can also take these 2 words, they're not defined terms here, but we could add non to the front of them to say things that are not collinear or not coplanar. So we have non-collinear would mean not on a line together. That would be like A, D, and F. So those are non-collinear because there's not a single line that passes through all 3. And on the last slide we saw that any 3 non-collinear points define a plane. So we can now use this defined term, non-collinear, to refine our definition of how we can find a plane. We need 3 non-collinear points to make a plane. And then non-coplanar just means objects that are not on a plane together. So if you think of the floor and the ceiling as being planes, right, they kind of stretch on their flat surfaces. Something on the floor and something on the ceiling are like on different planes. Last thing we're going to talk about here for today on defining terms is intersecting and coinciding. So intersecting, you're familiar with that with lines. So we take lines, they cross, we call that an intersection of the 2 lines. We can also intersect other objects within geometry. So it doesn't have to be 2 lines. We could take a plane and pass a line through it like that, and it would intersect where it pierces through it. So an example of this I like is basically take a sheet of paper, stab through it with a pencil, and you're intersecting a line with a plane when you do that. You can also intersect planes. So if I had a plane, and then I always struggle with how to draw this. I think it's like this, basically. We could intersect 2 planes with each other, and you could think of that as being like taking 2 sheets of paper and cutting a slit down the middle of one, and cutting a slit down the other side of the other, and kind of sliding them together so they make like a cross. So we can intersect planes with each other, lines with planes, lines with lines, and when we do, we basically end up with an intersection that is 1 step down in our dimensionality. So remember, lines are 1D objects, and when they intersect, we end up with a point, which was a 0-dimension object. So 2 lines are going to intersect at a point, and only 1 point. A line and a plane are going to intersect at 1 point as well. So we had a 2-dimensional object and a 1-dimensional object, and where they cross, we still have to step down. From this 1 dimension, we end up at 0 dimensions. But when we intersect 2 planes, they're going to form a line at their intersection. And remember, even though we draw these as parallelograms, these planes extend forever. So this line where they intersect is going to extend forever as well. So if we intersect these 2D objects, these flat planes, we end up with a line, a 1D object. So intersection doesn't have to be a single point like it was for our two lines. With this kind of higher level, like higher dimensionality, we can have more interesting intersections, and two planes form a line when they intersect. So you may be thinking we could also have two lines that are completely on top of each other, and then they don't just intersect at one point. But we actually have a different term for two things that are exactly on top of each other. That's what this coinciding word is. So if you think of a coincidence, things happening at the same time, right? You were at school, and some incident happened, so then they go and question you as to whether you were involved in that incident. So it was a coincidence you were at school at the time the thing happened, so those are just happening at the same time. Similarly, if I take one line and then I make another line that has basically the exact same equation, they're going to be coincident. They lie on top of each other. So these are coincident lines. We can also have a line and a plane that are coincident. So if I have a line that's lying on this plane, they don't intersect, they are coincident. Same thing if I have two planes that are exactly overlapping, they would be coincident as well. So we have these ideas of intersecting our basic geometric objects and then having coinciding objects. We're going to look at just a couple examples of these to wrap up our notes for today. So A says, how many planes are in this figure? So shown in the figure, we have one plane, which is, again, drawn as a parallelogram and named with this capital script letter S. So we have plane S. Okay, I'm still orange, apparently. Or we could name it by 3 points on the plane if we had 3 points, but we don't. So say I put another point E on the plane over here, I could also name that plane BCE, and that would be defining the same thing as S. It says name 3 points that are collinear. Remember, that means on the same line. So the only spot I have 3 points along a line together are A, B, and D. So we would say A, B, and D are collinear. It says, are A, B, C, and D coplanar? And explain. So that's a good question. We have A, B, D are all on the same line, so we know they're collinear, and then C is non-collinear. So we said this triangle would form a plane. So even though we don't have that plane drawn on the picture, they do lie on a plane together, and since this one is collinear, that would extend the same plane. So yes, they are coplanar, but the plane isn't drawn. So I'm not entirely positive what the book wanted as an answer here, but to me, yes, they definitely are coplanar, but they're not coplanar on S. They're coplanar on a plane that's not shown. Then it says, at what point do line DB, remember our notation with the arrowheads, and line CA intersect? So DB is this line here, and CA is this line, so they intersect at point A. We could actually know that without, no, we can't know it without the picture because they don't both have A in them. I thought it was DA and CA. If it said DA and CA, we wouldn't even need the picture. We would know that they both pass through A, but here we do need the picture. All right, so last examples for today. We have one more picture to look at. This one is a little more complex. It has a flat plane, like a table surface. Remember, the plane extends infinitely in X and Y for it. And then we have a pyramid sitting on top of the plane. The first question, I think, is a really complicated one. It says, how many planes appear in the figure? So I would say that we're only looking for drawn planes. So we know we have plane X, but we also have the faces of this pyramid, and each of those, if we extend it, is a plane. So we have plane DHG, which I could also call HDG, GHD, right? All those are the same. That's just one plane. We have this left side would be, I could call it JHD. We have this right side, front right side, which would be FDG. We have the back right behind there, which is FED. And we have the back left, which would be JED. So in total, drawn here, we have 6 different planes, although we could even define more if we were using planes that aren't drawn. So for example, FGM, kind of slanting down below our plane, would be another plane that's not currently drawn. But we'll go with 6 for our answer. It says name 3 points that are collinear. So we're going to look across our picture and try to find a line that has 3 points on it. Right here we have JKD, which has all of those on it. So J, K, and D all lie on that line. Remember, we could call that line KD or DK or JK or JD. Any of those names mean that same line. It says name the intersection of HDG with X. So HDG was this front plane of the pyramid, and X is the big flat table. So they intersect where they touch right here at line HG. So we're going to name that HG with our line notation. Even though HG is a segment, the intersection of that plane and that plane, if they went on forever, is going to be a line. So that intersection extends infinitely. It's not limited to this little length shown right here. This one says, at what point do line LM and line EF intersect? So LM and EF right here are going to intersect, well, nowhere, because this one goes in front of it and it's never going to touch, because in 3D, 2 lines can basically be not parallel and not run into each other. So they don't intersect at any point. And one of our defined terms we haven't talked about today, which I think we'll get to, is they are what we call skew to each other. So skew is something we didn't have when we talked about parallel and perpendicular in 2D, because on a flat plane, 2 lines always have to intersect eventually if we extend them forever. But in 3D, we can have 2 lines that are going different ways on different planes, and they never run into each other. So this is another defined term, which I think we'll get to when we talk about more stuff about lines in 3D and parallel and perpendicular. But I'll go ahead and introduce that here. And then our last question, are E, D, F, and G coplanar? So we have E, D, F, and G. So we said that G, D, and F defined a plane, and D, E, and F defined a different plane that intersects with it. So no, those can't all be coplanar, because we already defined 2 different planes that those lie on. So that's our notes for today. I'm going